The rolling boulder crashing down the mountain, that's kinetic energy. Kinetic, the boulder sitting high upon the mountain, that's potential energy. Potential energy in motion is kinetic. Energy that's waiting is potential. But whether it's kinetic or potential, both of them are energy. Olé! You stretch a rubber band and then release it, that's kinetic energy. Kinetic. You stretch a rubber band and then you hold it, that's potential energy. Potential energy in motion is kinetic. Energy that's waiting is potential. But whether it's kinetic or potential, both of them are energy. Olé! The heat that comes when gasoline is burning, that's kinetic energy. Kinetic, the energy that gasoline has stored up, that's potential energy. Potential energy in motion is kinetic. Energy that's waiting is potential. But whether it's kinetic or potential, both of them are energy. Olé!
In a jet plane, hot gases shoot out of the back of the engine at great speed. Energy for the motion of the gases is supplied by the burning of fuel. The action of the rushing gases causes an equal and opposite reaction, which sends the jet plane forward.
And that's how a jet plane flies. The law of motion applied to jets is simply action and reaction. The zooming power the engine gets is simply action and reaction.
The gas compressed inside the engine pushes out in all directions. Sideward thrusts are equalized and can't escape from the jet. Gas exhausted through the engine brings an opposite reaction, gives the jet its forward thrust. That's all there is to a jet.
The law of motion applied to jets is simply action and reaction. The zooming power the engine gets is simply action and reaction. Newton said it, give him credit. His law of motion still applies.
For every action, there is an equal and opposite reaction.
And that's how a jet plane flies. Among the many kinds of light rays, there's one called ultraviolet. And when you're thinking of this light ray, here's one thing you should not forget.
Ultraviolet rays are important in fluorescent lights, and they also cause sunburn.
Among the many kinds of light rays, there's also one called infrared. And when you're thinking of this light ray, this fact should linger in your head.
Infrared rays are very useful in broiling food and for heating.
Ultraviolet and infrared. Ultraviolet and infrared. Among the many kinds of light rays,
what are the others?
The spectrum of visible light ranges from red to violet. On one side of the spectrum are the infrared rays. On the other side are the ultraviolet rays. These are a small part of a much larger spectrum of electromagnetic waves. The complete spectrum of electromagnetic waves ranges from radio and TV waves through infrared to light, ultraviolet, and then to X-rays, gamma rays, and cosmic rays at the opposite end.
Ultraviolet and infrared. Ultraviolet and infrared. Among the many kinds of light rays, there are ultraviolet and infrared.
A fire releases heat energy, light energy, smoke, and gases. All materials are made up of tiny particles called molecules. When a chemical like wood is burned, its molecules rearrange themselves to form new combinations. A lot of motion and commotion of molecules results. This is heat. Electrons jump from orbit to orbit inside the atoms. This causes the light.
Mamma mia, what is this chemical energy? Mamma mia, what do they mean by that?
Hey, Bambino, why do you make it tough for me? Hey, okay, I'll try to answer that. When wood is being burned and it's combined with oxygen, then in the form of heat, it's giving off energy.
The energy released when particles of matter change. The energy released is chemical energy. Mamma mia, what is this chemical energy?
Hey, Bambino, what do you mean by that?
Mamma mia, why do you make it tough for me?
Hey, okay, I'll try to answer that. Each time you light a match or spark a motor's gasoline, the energy released is chemical energy.
The energy released when particles of matter change. The energy released is chemical energy.
Hey, Bambino, what is this chemical energy?
Mamma mia, what do you mean by that?
Hey, Bambino, try to explain it now to me.
Hey, okay, I'll try to do just that. When something's being burned and it's combined with oxygen, then in the form of heat, it's giving off energy. The energy released when particles of matter change. The energy released is chemical energy. Chemical energy.
How do we measure energy?
In foot-pounds, foot-pounds.
How do we know when it gets to be
A foot-pound, foot-pound. The energy expended by lifting 1 pound 1 foot high. That's 1 foot-pound. That's 1 foot-pound. The foot-pound measures energy.
Pick up an object from the ground.
Easy does it.
Say that the object weighs 10 pounds.
10 pounds, 10 pounds. Lift up the object 4 feet high. 10 by 4 you multiply. That's 40 foot-pounds. 40 foot-pounds. The foot-pound measures energy. The foot-pound measures energy.
A rock looks so still, but is it? The rock is made of tiny, invisible particles called molecules. These molecules vibrate rapidly. The molecules are made of atoms. In the atoms, electrons whiz around at tremendous speeds. There is plenty of motion in the rock and in everything else, and that motion is energy.
Stars and waterfalls, motors and bouncing balls, sunlight and sound and air, moving continually are proving conclusively motion, motion everywhere. Rocks and minerals, insects and animals have one thing that they all share. Moving continually, they're proving conclusively motion, motion everywhere. Clouds and jumping beans, roses and evergreens, dishes and silverware, moving continually are proving conclusively motion, motion everywhere. Take a look at me, what are you sure to see? Muscle, skin and teeth and hair, moving continually, they're proving conclusively motion, motion everywhere. Here's a thumbnail introduction to atomic energy. Here are some important highlights of atomic history, from the X-ray and electron and the quantum theory, down to Einstein and his formula for mass and energy. Hip hooray, we've got atomic energy. It could mean a better world for all. Hip hooray for those who made it come to be. May we present the main events and heroes great and small.
1896, France.
Henri Becquerel finds that uranium ore is radioactive.
1905, Switzerland.
Albert Einstein shows that energy and matter are equivalent. E equals mc squared.
1913, Denmark.
Niels Bohr explains how atoms emit light as electrons jump from higher orbits to lower ones.
1938, Germany.
Otto Hahn and Fritz Strassmann split the uranium atom.
1942, United States of America.
Enrico Fermi builds the first atomic pile and shows that atomic energy is practical.
Hope and pray we use the power constructively to bring about a peaceful world for people great and small.